Hey, what's up YouTube? In this video, I'm going to give you an overview of a Niagara system I built to create a GPU-based swarm, using particles that can be converted into CPU-based AI agents and then back into particles. The system includes obstacle avoidance, avoidance of nearby particles, player avoidance, and more. This is a follow-up to my previous Niagara state machine video, where I explained how to build a custom state machine to drive vertex animation directly in the shader. No, this is not a tutorial, it's more of a breakdown, where I'll walk you through the core ideas behind how the system was built. I won't go too deep into the exact implementation details, because building AI logic on the GPU, especially in Niagara, really depends on your specific use case. It's hard to come up with a one-size-fits-all solution. My implementation was designed specifically to solve my own problem and tailored to the needs of my project. So the details are not as important as understanding the overall concept. Alright, let's dive in. Let's start with a quick overview of the Niagara system. At the system level, I created a neighbor grid 3D interface, along with the world to unit matrix needed to map particle world positions to grid unit space. I've made an in-depth video about the neighbor grid 3D interface already, so I won't cover it again here. In short, the neighbor grid 3D is a spatial structure that lets you write particle indices into grid cells, and then, based on a particle's position, you can find the cell it's in, query the cell's data, and retrieve the indices of nearby particles. It's essential for algorithms where particles need to be aware of each other. At the emitter level, I create all the interfaces I'll be using. These include an attribute reader, a vector to the animation array that stores the frame and duration of each animation, baked into a bone animation texture using my GameTools Blender extension, which I have also covered extensively in previous videos. Export particle data, an interface used to send the data to blueprints. Memory buffer, which serves a very specific purpose I'll explain later. And a Niagara data channel, which I'll also come back to. For now, we'll keep things simple and go step by step. I've disabled almost everything and will only enable components as we need them. So during the emitter update, I'm only updating the emitter state, nothing else. On particle spawn, I simply initialize all the variables I'll be using to their default values. Nothing fancy. I'll skip this stage. Now, the swarm logic is almost entirely contained within a single simulation stage. There's nothing happening in the particle update stage, as you can see. I used to structure things differently, but I found this approach to be much simpler. Previously, I used simulation stages for specific tasks, like querying the neighbor grid 3D interface. The issue was I had to store the results and wait until the next tick to use them in the particle update stage, which made data flow less than ideal. By doing everything in a compute stage, I can, for instance, control exactly when the neighbor grid 3D is queried, and I don't have to store results in persistent variables. They can just be transient, existing only within the stage. Much better, in my opinion. Anyway, let's dive in. The first few modules are designed to provide some initial context for the state machine and movement logic, so let's begin with this first module. In this one, I sample the global mesh distance field at the particle's current position and use it to derive the surface normal. This will later help me figure out if the surface the particle is standing on is walkable or not. And I'm not doing anything with this data yet, it's just written into transient variables for use in later modules if needed. The same goes for sphere tracing. I'll keep it brief here since I've made a follow-up video focused entirely on sphere tracing. It's already available in early access on my Patreon and will be released on my YouTube channel in a couple of days. Essentially, sphere tracing uses the global distance field to perform a kind of ray tracing. This allows particle to detect incoming obstacles. Again, I'm not using this data yet, it's just stored in transient variables for now. Next, I have a module that generates a random unit 2D vector, nothing fancy. Then this is simply a renamed curl noise force module, Now, it's not used to add a force of any kind. See, it doesn't write to any intrinsic physics parameters. It simply samples the 3D noise texture and gives me access to a random vector that changes smoothly over time. I just make sure to offset the seed per particle so that nearby particles don't sample the noise texture at the same coordinates. And that's it for the prerequisites. Let's start by talking about how the animation is handled. The skeletal animation is baked into bone animation textures using my free Game Tools extension for Blender. It comes with a detailed wiki that explains how the skinning and bone animation data are baked into textures, which are then sampled in the vertex shader to reconstruct the skinning and play back the animation. I won't go over that here. Long story short, this lets me render a static mesh that's animated using a lightweight vertex shader, making it possible to render hundreds, if not thousands, of particles to create a swarm. Now, in the last video, I showed how a state machine could be used to drive vertex animation textures. Its sole purpose was to control animations, deciding when to transition to a new animation, loop the current one, and so on. It was quite minimalist and as such limited, right? This time the state machine I've built works a bit differently. It's no longer tied to the duration of an animation or anything like that. Instead, it defines the actual states a particle can be in, like idle, move, excited, and so on. That distinction is important because now each particle state can trigger different animations. In a way, there are two state machines working together, one that controls the particle's state, and another that determines which animation to play based on that state and calculates which frame of the animation should be played. That said, the core idea behind driving the vertex animation is still the same. The shader is told which frame to play using material dynamic parameters. And all of that is handled in this custom module. Here I cache the animation that's currently playing. Next, based on the particle's most up-to-date state, I select which animation to play. Most states have a single looping animation, but the excited state, for example, can randomly choose between two, one called wave and the other excited. This selection happens when a new state has just been set during the current tick. Then I simply compare the two animations to determine if a new one is playing, or I force this to be true when the state changes. Next, I cache the current animation frames before updating them, so the shader can calculate the previous vertex offset using a previous frame node and use it to output velocity based on the movement delta. Then I sample the animation start frame and length from an array set at the emitter level. Next, I increment the animation frame, making sure it loops properly based on the current clip length. I do the same for the next frame so the shader can perform linear interpolation for smoother animation. If a new animation is played, I reset the animation frame to the starting frame of that animation. All of this is sent to the shader, which uses it to sample the bone animation textures. And that's pretty much it for the vertex animation side of the system. Since it's all driven by the particle state, let's take a look at how that state is computed. I created a blueprint enum listing all the states, which is registered in Niagara, so I can use it to create an enum variable describing the particle's current state. If I highlight that variable, its first use in the particle update stage is here, in the pre-evaluate state module. This custom module begins by caching the current state before making any changes. Next, I calculate the state time and check if it has exceeded the state's duration. If it has, the state should end. This transient variable is important and gets reevaluated in later modules. Generally, the common condition for any state to end is its duration, but additional conditions can be added for specific states. More on that shortly. Once this value is computed, I reset the state time overflow to a safe value, ensuring it remains positive and within the animation's length bounds. Finally, I convert the particle's position to local space, relative to the emitter's origin, to determine its distance and direction. The distance is normalized here based on a user-defined variable that sets the emitter's overall radius. If the particle gets too far from the emitter, I consider it off bounds. This is important because I'm using a neighbor grid 3D interface to compute nearby particle avoidance, which requires the emitter to be spatially limited for all features to work properly. Basically, I don't want particles wandering off infinitely, and this variable helps drive logic to prevent that. So with these basic transient variables, I can evaluate what should happen to the particle state during this update tick. And to keep things organized and readable, I created a custom module for each state. They all follow the same pattern. Is the particle currently in that state? Was it in that state in the previous frame? If not, this means it's a new state. Next, I reevaluate the state's end condition. For example, the module handling the idle state checks if the particle is indeed in idle and whether it should end. Remember, the initial end condition checks if the state time exceeded its duration. As a safety measure, any state can be exceeded immediately upon entering, but after that, for the idle state specifically, it's strictly driven by duration, so it can exit without extra checks. So do we actually exit idle? And if yes, what state should we transition to? The idle state may transition to another idle or to pivot, meaning turning in place. If the particle is within the emitter bounds, it can transition to move, otherwise it's forced into pivot so it can rotate back towards the emitter's origin and eventually return within bounds. And that covers the idle state. The same logic structure repeats for each other state. For pivot, are we in pivot and were we in pivot last frame? The pivot state ends if it exceeds its duration and the particle has pivoted enough. If we exit pivot, what's next? If off bounds and the particle is facing the emitter's origin sufficiently, it can transition to move, otherwise it pivots again. The move state module is similar. If the particle remains stuck in move for too long, there's a safety exit, and move can only transition back to idle. Finally, the excited state has some additional logic. I provide the player's spawn position and a radius through user parameters set in a blueprint. In the character blueprint, I get a reference to the blueprint that manages the swarm VFX. Then I start a timer that periodically sends the character's location to that blueprint, and then in turn to Niagara. Back to Niagara, first, are we in the excited state? If not, should we be? This depends on the particle's proximity to the player and the last time it was excited, to avoid triggering this state too often. If the particle should be excited, the state is forced to change. If newly excited, I log the current time, and this later allows me to check that condition for entering this state, right? Now, the excited state can only end if its current animation has just finished playing, to avoid an abrupt cutoff. Honestly though, this part is pretty sketchy and could use a proper rework, but I've already spent enough time on this system, whatever. The problem is that, depending on the frame rate and other factors, there's no guarantee you'll land on a timestamp within 0.1 seconds of the animation's end, so the condition might keep returning false, causing the state to persist indefinitely. But it's good enough for a prototype, I guess. Anyway, I also check the distance to the player, and if it gets too far, that, along with the state's duration, determines when the excited state ends. And from excited, the particle can transition either to idle or pivot, depending on whether it's in bounds. After evaluating all these conditions and determining if the particle should change state, I compute a few more things. Has the state actually changed? If yes, log the time of the change. And reset the state time accordingly. At this point, I have all the information needed to drive various logic. Which state the particle is in, how long it's been in that state, is it new, has it ended, and more. Alright, I'll come back to those two modules in just a minute. For now, let's focus on what a particle does on its own before we worry about how it behaves in relation to nearby particles or the pawn. Now, here I compute the direction the particle should face, and this obviously depends on the current state of the particle and whether it has just changed state. If it's in the excited state, the particle should face towards the player to wave. In the pivot state, if the particle is out of bounds, it should face towards the emitter's origin to avoid wandering off infinitely, otherwise it's allowed to face in a random direction. I also check if the particle is facing an obstacle directly in front of it, and if it is, I try to steer it away. The movement direction is a bit more complex and could definitely get some more love, but whatever. Here I'm basically trying to safely offset the direction based on how close it is to obstacles detected by the sphere trace. I'll skip the math since this is far from being perfect. And here, if the particle is within bounds, I add some noise from the curl noise force module to randomize its trajectory a bit. Finally, that offset gets added to the direction I want it to face. Note that this still allows particles to temporarily go out of bounds during the move state. Once that ends, they switch to the pivot state, which reorients them so that the next move state steers them back in bounds. Anyway, the target forward vector is set when the state changes, but it's also updated every tick during the move and excited states, so the particle can keep facing the player as it moves and continuously adjust its movement direction based on noise, proximity to obstacles, and other factors. The pivot state is the only one that sets the target forward direction, only when entering the state just once to choose a new direction. Then I interpolate between the current forward vector and the target one. The interpolation speed can be varied based on the current state. One final step, I interpolate a vector I haven't mentioned yet, called the avoidance vector. This is applied as a simple offset to the forward vector to create a new transient vector. The important thing to note here is that this transient vector will be used to apply movement and mesh orientation, not the original target direction. That's because when particles need to avoid something, I don't want to alter the direction they originally intended to go in, just modify it temporarily. So the target direction stays the same and only gets offset when necessary to produce a new vector. Hope that makes sense. Next, I compute the minimum and maximum allowed slope angles to determine whether the surface the particle is currently standing on is walkable based on its normal. If it's walkable and the particle is in a move state, I calculate its movement speed, which is reduced the steeper the slope. I also cache the previous position before modifying it. That's important. Then I apply the movement. Position plus the movement direction multiplied by the speed. This speed is slightly reduced if the particle is heading directly toward an obstacle. Next, this part might look a bit complex, but all I'm really doing is comparing the speed I just calculated to the actual speed the particle is moving. If there's too much of a difference, it means something's off. Most likely the particle is stuck, so I increment some kind of value. If everything's fine, I decrease it. So it's not really a timer, more like a heat value that goes up and down depending on how likely it is that the particle is stuck. And remember, that's the value used here to stop movement if the particle is stuck, to ideally pivot away from obstacles and find another direction. Next is the animation module, which I've already explained. Here, if the particle is changing state, I compute a new duration for that state. Most states use a randomized duration. The excited state, however, uses the length of its animation and plays a random number of cycles to avoid cutting the animation off abruptly. Finally, based on the forward vector and an up vector, I compute the mesh orientation. And this is specific to the default orientation of my static mesh. One more thing, oh yeah, I derive the particle's actual velocity from its position delta. And that's it for the basics. At this point, on a flat surface, the particle should behave on their own, wandering around, pivoting, staying idle, and waving at the player. Cool, but right now, particles are oblivious to the player and to each other. There's no obstacle avoidance, terrain awareness, no particle avoidance, nothing fancy yet. So let's see how we add that. I used a neighbor grid 3D interface to query nearby particles. Nothing fancy. I actually made a very thorough video explaining everything you need to know about this interface, so I won't go over it again here. Basically, the grid is populated with particle indices during this first simulation stage. And once the grid is filled, it can be queried in the second simulation stage. Let's take a quick look at the code. I start by getting the grid cells that the current particle is in. With that cell, I iterate over each surrounding cell, including the cell itself. However, there's no need to check all 8 neighboring cells if you ensure that the cell's width is greater than the particle's diameter. Instead, you can check whether the particle is to the left or right of the center point of its current cell, and only check the corresponding neighboring cell, not both, because the cell width constraint guarantees it can't overlap with both at the same time. The same logic applies to the top and bottom cells as well. Anyway, for each overlapping cell, and for each particle those cells might contain, I retrieve the particle's index. If it's not the current particle, I get the other particle's position and compute the position delta between them. I compute the squared distance between them, check if the other particle is close enough for any proximity effect to kick in, and if it is, I derive the direction and distance to the other particle. That information is then used to resolve the overlap by pushing this particle away. The other particle will do the same when it's processed, so both gradually push each other apart over time to resolve the overlap. Nothing unusual. This is just for particles that are physically overlapping to some extent, but I also wanted particles to proactively avoid each other while moving. To do this, I first make sure this distance threshold for the avoidance effect to kick in is non-zero only when moving. If so, I project the offset between them along the particle's forward direction. It's kind of like raycasting forward, and if the other particle is too close to that ray, it means it's in our path and should be avoided. And the resulting offset can be used to deviate the forward vector, causing the particle to turn away from the incoming particle. It's a bit of a hack, and there are definitely more robust ways to handle this, but for this example it does the job. The thing is, we might encounter many particles ahead of us, and we don't necessarily want to avoid all of them equally. For example, we might not care as much about particles that are further away. So essentially, what I'm doing here is computing a weighted arithmetic mean, if I'm not mistaken. See, this value is incremented by the projected offset, weighted by factors like the distance between particles, the projected distance on the ray, the velocity delta, and visibility. They each contribute to the final weight. The result is a vector that is smoothed over time, and it can be visualized using sprite renderers with custom bindings. So what you're seeing here is essentially the vector that gets added to the forward vector, causing the particle to momentarily deviate from its original path. Next, to handle pawn collision, I simply forward the pawn's current location to Niagara through a blueprint using a user parameter. Once I have the pawn's position in Niagara, I compute the delta between the pawn and the particle, and if they are too close, I push the particle away from the pawn. Implementing a two-way interaction, where the pawn's movement abilities are reduced the more particles it pushes around, is technically doable, but I think it would be pretty challenging to implement properly. That said, a quick hack could be achievable. you'd probably need to send the positions of the pushed particles from the GPU to the CPU using a readback event, assign each particle a weight, and then compute opposition forces to apply to the character's capsule based on its own weight, similar to how the character movement component handles interaction with physics objects. A simpler workaround might be to just reduce the pawn's movement speed based on the number of particles it's interacting with. But anyway, that's outside the scope of today's video. Now, even after all that, the particle still doesn't know anything about its surroundings or what surface it should be standing on, right? That's handled here. Particles can use either the distance field for projection and obstacle overlap solving, the landscape, or both. Here I sample the global distance field and project the particle's position onto the nearest surface. Then I derive the surface normal at that location. If the surface is not walkable, I project a down vector onto it and use the result to offset the particle's position, making it slide downward along the slope. The same logic applies when projecting onto the landscape. I sample the height and project the particle's z position onto it. Then I sample the landscape's normal, and if the slope is too steep, the particle slides down along it. And this gives us the kind of results you're seeing here. It's important to note that solving particle-particle overlaps first, and then resolving overlap with the player, might cause some particles to end up overlapping again, because they get pushed around after the initial resolution. The same goes for surface projection. Solving one constraint can break another that was already handled, since everything is applied sequentially in a simple pass. That's usually fine though, since this logic runs every frame, the system tends to converge to a stable state pretty quickly. You could run multiple iterations per frame to speed up conversions, but that comes at a cost. Personally, I don't think that's necessary. This kind of swarm VFX is typically allowed to be somewhat approximate. It's not meant to be physically accurate. Anyway, that gives us a system that feels a bit more real and grounded, because the particles are now reacting to their surroundings, to each other and to the player. It's still a rough starting point, and there's definitely plenty of room to take this much further, but it's good enough for the purpose of this video. That said, there's still one more feature missing. Right, so this swarm system was kind of an excuse for me to try something that had been on my mind for a while. The idea was to read back particle data from the GPU in order to kill those particles and replace them with quote-unquote particles on the CPU for gameplay or other purposes. This isn't a novel approach by any means, and I know it's often used, though I can't recall a specific example off the top of my head. I do know Kena Bridge of Spirits used something similar, though in that case, particles were kept on the CPU side, probably to simplify things since GPU readbacks come with annoying quirks. And I'm not confident in recommending the approach I'm about to demonstrate without first considering simpler, more stable alternatives. I'll touch on that more in a minute. Anyway, I hadn't had the chance to experiment with this myself, so I wanted to give it a shot. My goal was simple. Cast a ray from the center of the screen to quote-unquote select a particle. Then, based on player input, the selected particles could be converted into CPU-based AI agents for gameplay purposes. Now, there are many ways to approach this, but I think it boils down to two main strategies. One, you fetch all the particle positions, radii and other relevant data from the GPU and perform the raycast on the CPU. Two, you send the raycast data, origin and direction, to the Niagara GPU system and perform the ray test inside the emitter at the particle level. Starting with the first method, where particle data is transferred from the GPU to the CPU, the downside is memory bandwidth and latency. Reading back large amounts of data from the GPU can be expensive-ish. Also, doing the raycast on the CPU, especially with lots of particles, may require some kind of acceleration structure, or at the very least, a performant C++ implementation. Blueprint is not recommended for this. The upside is that gives you full control. You can ensure, for instance, that only one particle is quote-unquote selected, or apply custom rules when processing the raycast results. Once you identify a hit, you can spawn an AI agent on the CPU and send the index of the selected particle back to Niagara to destroy it, essentially doing the GPU to CPU switch. As for the second method, where the raycast data is transferred to the GPU for computation, the downside is that GPU parallelism makes this more difficult. Each particle computes the ray test independently with no awareness of other particles, so ensuring that only the closest particle is hit becomes a real challenge. The upside is that this method can be extremely efficient to some degree. You only send the indices of the selected particles to the CPU, and the cost of the raycast itself is likely massively reduced thanks to parallel processing. That being said, I hate making absolute statements about performance. It's never as simple as saying this is performant and that is not, especially when comparing CPU and GPU solutions. You could be heavily CPU bound and get away with using an unoptimized, expensive brute force GPU algorithm essentially for free, so the whole debate can be misleading. Anyway, I chose the second approach, doing the raycast on the GPU, mainly because it was an opportunity to try something new. Now, I won't spend too much time on this part, because I'm definitely not an expert in GPU programming, and I don't want to pretend I'm qualified to teach this in depth. I just want to show you what I came up with. So the core challenge here is ensuring that only one particle gets hit by the ray. And once again, I've got DeathRay to thank for suggesting a possible solution. I also don't claim that this is even a problem worth solving. You could probably work around it with some creative design choices. But again, I was merely interested in the challenge and wanted to see if I could make it work. So here's what I did. I sent the Niagara system the ray origin and direction, which are used in this module to project each particle's position onto the ray. I then compare the projected distance to the particle's original position to check if it's within a certain radius. If it is, the ray intersects the particle, making it a candidate for selection. Now it's just a matter of finding not only which particles are hit by the ray, but specifically the first one that's hit. This is handled using the memory buffer interface to store two values, one for the index of the closest particle, and one for the float bits representing the depth of that closest particle. But thanks to parallelism, it's not as simple as writing this data directly into the memory buffer. So here I retrieve the minimum depth of all particles processed in the same wave. And if this logic is executed on the first wave, only then we continue. I reinterpret the bits storing the float depth as an unsigned integer. Then I get the bits currently stored in the buffer and begin a spin lock, which is basically a way to emulate a mutex on the GPU as far as I understand. It makes the thread repeatedly check a condition until it either succeeds or fails, helping prevent race conditions between threads. It's a bit beyond my expertise, so I won't go deeper into it to avoid giving wrong information. But the gist is, by the end of this simulation stage, the memory buffer holds the index of the closest hit particle. From there, all I need is another stage to read that index, compare it to the current particle's index, and if they match, that's our hit candidate. And that could be enough to say this particle is selected. But on top of that, I add a small timer mechanism because why not? If the timer exceeds a set threshold, the particle is officially selected, unless we decide to clear our selection. By debugging the selected state using particle color, we can visually confirm that everything is working. Next step, the GPU-CPU swap. One of the painful parts of this approach is the latency. Sending data from the GPU to the CPU, and vice versa, usually introduce a 1 or 2 frame delay. So if we immediately kill the selected particle on the GPU, and then send the swap data to the CPU, the particle might disappear for 1 frame or 2 before the swap completes. To mitigate this, I introduce a 1 frame delay using a boolean I call pending kill. If it's true, the particle should die, otherwise it stays alive. If a particle is selected and we receive the input for the swap from a user parameter, I use the export particle data interface to, export its data. Position, animation frame, and forward vector. If the export succeeds, the particle is marked as pending kill and it's no longer part of the selection. On the next frame, the particle will be killed, and by that point, hopefully, the blueprint should have received its data to replace it with a CPU-controlled agent. And that's done using the straightforward export particle data interface. You just need to create an object user parameter, set it to self in the blueprint that should receive the data, and implement the readback interface providing this function. And that's it. I've covered GPU readback with Niagara in many videos, so I'm only touching on it briefly here. Long story short, I'm spawning a character blueprint matching the GPU particle's position and orientation. That character simply checks whether the actor is moving or not, and updates the animation frame accordingly. The frame data is stored in the mesh's custom primitive data, so it can be accessed in the shader. It's almost identical to the Niagara approach and material. Anyway, that character is possessed by an AI controller. Now, I recommend using state trees when building AIs. Unfortunately, at least in version 5.5, it's been very unstable for me. Frequent crashes make it unusable, so I'll wait for 5.6 to try again. For now, I'm sticking with good old behavior trees. In a nutshell, that means running the behavior tree when the character is possessed, and writing all the necessary initial data to the blackboard. For instance, this agent is meant to follow the pawn at first. Here I send a reference to the swarm system it should belong to, its initial spawn location, a reference to the pawn, and any other data that might be useful for building the behavior tree. The blackboard is also updated every tick to keep track of the pawn's current location. I'm not an expert in behavior trees, to be honest. I just know how to get something working. It might not follow best practices. When needed, I can also send all agents back to the swarm with a simple input. That's done by setting a boolean in the blackboard. If the AI agent needs to follow the player, it moves towards them, otherwise it simply looks at the player. And this is a custom task that sets the actor's rotation to face the player, unless the player moves too far away, in which case the task ends, allowing the move to behavior to resume. If the agent is instructed to rejoin the swarm, it moves to a location stored in the blackboard at spawn time, which is the particle's initial position when the swap occurred. Once the task either succeeds or fails, a custom task sends a signal to the swarm blueprint, passing along a reference to the agent that needs to rejoin. I write the necessary data into a Niagara data channel and start a one-frame timer to destroy the CPU agent. That Niagara data channel is then read here to spawn particles, and initialize them with the correct data. Position, forward vector, animation frame, and state. And that is the GPU to CPU to GPU swap mechanism. Oof. Now, this is cool and all, but I feel like using this kind of technique can be risky for several reasons. The main reason to simulate the swarm on the GPU is because it's often just too expensive to run on the CPU. So, precautions need to be taken when handling the swap to avoid converting every single GPU particle into a CPU agent. Otherwise, we might as well do a CPU swarm to begin with, right? So one solution is to use the simple counter interface to atomically increment a counter whenever a particle is selected and reset it when the selection is cleared. Then simply prevent any additional particles from being selected if the count exceeds a certain threshold. You can also track how many CPU agents have been spawned on the CPU side and use that to update a counter on screen. Also, what if spawning the CPU agent fails due to collisions or other conditions not accounted for in the GPU system? You'd need a way to handle that, ideally by reverting the swap in some way. And what if the navigation mesh is invalid at the location where the particle is converted, making the CPU agent unable to move? Or what if it can't return to its original position when asked to rejoin the GPU swarm? That's actually one of the reasons there's no spawn module in this emitter. No spawn burst, no spawn rate, and so forth. Instead, all of that is handled on the CPU, where I use a nav mesh to find valid random locations and send that data to Niagara through the same data channel used for the CPU to GPU swap. This way I can at least ensure the particle's initial position is valid. From there, I just have to rely on my obstacle overlap solver and slope handling to prevent particles from ending up in weird or invalid spots. So yeah, lots to consider as always. Nothing's ever easy in game dev. Still, this can lead to some really cool gameplay mechanics, and even without the GPU to CPU conversion feature, this is still a solid example of a performant and visually decent swarm in Niagara. The sky's the limit with Niagara. You can build an entire game in it at this point. Alright, that's it. I hope you found the breakdown useful. Files are available as a tier 3 reward on my Patreon. Thanks for watching, and thanks to my generous Patreon community for the ongoing support. Consider leaving a like and subscribing to the channel. I'll see you in the next one. Take care of yourself. Bye bye!